I will present some recent results from a paper submitted and accepted to IFAC World Congress regarding hybrid modeling of a virtual flow meter. So I've been focusing on modeling the petroleum production choke, which may be illustrated as this figure shows. And the result or the goal is to model the oil flow through the choke using nearby measurements such as pressure and temperature. So you want to do this hybrid, and that is to combine two known modeling methods, mechanistic modeling, which is based on first principle and physical laws, together with data-driven or AI modeling that utilizes the increasing amount of process data in the petroleum assets. But to model it hybrid, you can do it in numerous ways. And if you place all the hybrid models on a scale from fully mechanistic to fully data-driven, I've been working in this domain here. So I've utilized a mechanistic model as a baseline and then inserting some data-driven elements into the model to make it more hybrid. So we want to do this to preserve the interpretability of the model, and that is to retain physical interpretation of the model parameters. But we also want to increase the flexibility of the model, and that is to increase the ability to adapt to unknown or even unmodeled physical behavior of the model or the process. All right, so what I've done is to use this Kittelsen model, a mechanistic choke model as a baseline, and then I've used neural networks to estimate some of the parameters in the model. So this is a type of serial model. The results I'm going to present is from a case study on the petroleum asset Edvard Grieg, and I've been modeling 10 oil wells here, and we compared 3 model types, and the first one is a fully mechanistic one. This is the Kittelsen model, and the second is a fully data-driven one, which is a neural network. And of course, the hybrid one is a combination of the two above, where we use the Kittelsen model and then we model the CV curve, a property of the choke, as a neural network. So the results are neither too good nor too bad, and there's a lot of work still remaining in this domain. You can in general see that we have very large errors, but this is the same for all the models. So you can see that for around 70% of the test points we have a deviation of 20% or less for all the models. However, we would like to have it around 90% performance on 10% deviation. That would be the ideal. However, you can see that for the fully data-driven models, we have some outliers that does not occur in the hybrid models. And that may indicate that the hybrid models may have preserved some of the extrapolation abilities from the mechanistic models. Further, you can see that for some of the wells that I modeled, the hybrid model is actually providing the best performance overall. Yet, when you look away from the outliers, you can see that the data-driven models is the one that has the best performance overall, and therefore there's a lot of work still remaining in this domain, and I'm still focusing on choke modeling with different types or different variants, and we try to estimate some other parameters with neural networks as well. All right, so this paper and the results can be found for now at ArcSci. However, as I said, it is submitted and accepted to IFAC World Congress and will be available at IFAC Papers Online eventually.